I'd now like to work through this example, demonstrating that A4 has no subgroup of order 6. The proof is not something that can be adapted extremely easily to other cases, but it is something that we can understand, and it reviews a lot of important concepts, so we're going to cover it. In order to get a handle on what's going on in A4, let's first take a look at the elements of S4, the entire complete permutation group on 4 letters. And let's look at the permutations according to their cycle structures. So the first cycle structure that we have is the identity. This does happen to be an even permutation, and there's exactly one identity element in any group. Then we move on. It's possible that the cycle structure of the permutation is just a single transposition, which we're going to denote by A maps to B and B maps back to A in disjoint cycle notation. It could also be the case that these 4 elements are partitioned into a pair of transpositions, AB and CD. There could be a unique fixed point where the remaining 3 elements form a 3-cycle, ABC. Or lastly, all 4 elements could be in a 4-cycle together, which we'll denote by ABCD. And these are this is the set of all possible things that could be happening in S4. And all we have to do now to figure out the elements of A4 is go through these and determine which cycle structures are odd and which are even. So we have seen that the identity is an even permutation, so the identity belongs to A4. Better, since A4 is a subgroup. AB, that's a single transposition. 1 is an odd number, so that is odd. However, ABCD is 2 transpositions, so that belongs to A4 as well. All permutations with that cycle structure. And when we take a 3-cycle and write it as a product of transpositions, it turns into 2 transpositions, ABAC. So we would write that, and so that is also even. ABCD is a product of 3 transpositions, ABACAD, so that is an odd element of S4, and so it doesn't belong to A4. So I've just summarized what we've said, the 3 different cycle structures that belong to A4. I've got them listed in this table here. In the next column of the table, I've listed the order of an element having that particular cycle structure. So the identity has order 1, as always, and then there's exactly 1 element of order 1, since there's only 1 identity. When we move on to the permutations, AB as 1 transposition and CD as another, the order of that element will be the least common multiple of the cycle lengths, which is 2. Each of them has 2. Least common multiple of 2 and 2 is 2. And a simple counting argument reveals that there are exactly 3 permutations inside of S4 that have this particular cycle structure. And similarly, when we go look at the element ABC, which is just a 3-cycle with a fixed point inside of A4, this has order 3 since the cycle length is just 3 by itself. And another simple counting argument reveals that there are 8 elements, 8 permutations that have this particular cycle structure. And sure enough, we can double check our arithmetic to add up that 8, 3, and 1 makes for 12, which is the number of elements inside A4. And now we want to use this information to argue that A4 does not have a subgroup of order 6, even though 6 is a divisor of 12, which is the size of A4. So let's argue by contradiction. Let's suppose that H is a subgroup of A4 and that it does have order 6. Now, what we want to do is we want to pick a permutation alpha inside A4. I don't know what it looks like, but I want alpha to have order 3. It's not a problem. A4 has plenty of elements of order 3. In fact, A4 has 8 elements of order 3. So I can be a little bit more specific in the way that I pick alpha. In fact, I can pick alpha so that it does not belong to this subgroup H. And that's a simple pigeonhole argument, right? A4 has 8 elements of order 3. H is a subgroup with just 6 things in it. I can't fit all of my elements of order 3 inside H, so there has to be one that does not belong to my subgroup H. Now, using that formula that we had before, the order of the group is equal to the order of the subgroup times the index of the subgroup. If we're supposing that H has order 6 and A4 has order 12, then it must be the case that the index of H inside of A4, which is the number of cosets, is 2 by a simple division. So there are 2 cosets of this subgroup H inside of A4. Now let's look at the subgroup, the cosets that I would have, right? H is one of my cosets, alpha H is certainly one of my cosets, and alpha squared, that's neither, alpha squared H is another coset. Alpha squared is not the identity, it's not alpha. And so we have these three distinct cosets, these three cosets, H, alpha H, and alpha squared H. These are three cosets, but since there are only two cosets of H inside of A4, at least two of them have to be the same. So let's go through and let's figure out, what we'll do is we'll arrive at a contradiction by any one of those pairs of cosets being the same. So first off, if H is equal to alpha H, we get an immediate contradiction. Alpha is certainly a member of alpha H, and since alpha H is equal to H, we would conclude that alpha belongs to H. And this is a contradiction to the way that we've chosen alpha. We've explicitly chosen alpha so that it does not belong to the subgroup H. Now we get exactly the same contradiction if we are to assume that alpha H is equal to alpha squared H. It will get the same equality, H is equal to alpha H, by just multiplying both sides of this equation on the left by alpha inverse. So the last case we need to consider is that if H is equal to alpha squared H, and here is where we're going to use the fact that alpha has order 3. So if we were looking at the group generated by alpha, since alpha has order 3, we would list out the group generated by alpha as the identity, alpha to the first power, and alpha squared. And then as soon as we hit alpha cubed, we'd be back at the identity. It follows that alpha squared is actually equal to alpha inverse. And so since alpha squared belongs to the coset alpha squared H, and we're assuming that H is alpha squared H, we conclude that alpha squared belongs to H. But alpha squared is really alpha inverse, remember, since alpha has order 3. And if alpha inverse belongs to H, and H is a subgroup, then alpha inverse's inverse, which is alpha, is going to belong to H as well. It's by closure under inverses, since H is a subgroup, if alpha inverse belongs to H, then alpha belongs to H. And that's the same contradiction that we reached in these other two cases. So we explicitly chose alpha so that it did not belong to the subgroup H, and the contradiction we found was that no matter what, we forced alpha to belong to H. And so we see that it's not possible for A4 to have a subgroup of order 6. Now I'd like to conclude this set of slides by just doing one last example, applying LaGrange's theorem and actually applying what we've just learned. So let's show that if H is a subgroup of S4, and H happens to contain the permutations 1, 2, and 2, 3, 4, then it must be the case that H is equal to S4. Now before we learned about LaGrange's theorem, or just if we didn't really have a lot of direction with this problem, S4 is not really the biggest group around. We could just start brute forcing with closure and seeing what other elements we got by combining 1, 2, and 2, 3, 4. But this is probably not the best way to go. I mean, that's a fishing with dynamite type solution to this problem. Let's use LaGrange's theorem to figure out that H must be equal to S4. So one place where we might start is we might take a look at the order of the permutation 1, 2 and the order of the permutation 2, 3, 4. So 1, 2, that permutation has order 2, and the permutation 2, 3, 4 has order 3. And we know that the order of these elements has to divide the order of this subgroup. So since 1, 2, and 2, 3, 4 belong to H by assumption, we know that 2 has to divide the order of H and 3 has to divide the order of H. And we conclude that the order of H is at least divisible by 6. So there are at least 6 things inside the subgroup H. We can take this idea a little bit further. If both 1, 2, and 2, 3, 4 belong to H is a subgroup, it has to be closed under our group operation. So when we take 1, 2, and 2, 3, 4 and combine them, this also has to belong to H. And it just so happens that when we take 1, 2, and 2, 3, 4 and combine them, we get an element, a 4 cycle, which has order 4. So 2 and 3 must divide the order of H, but in fact 4 and 3 must divide the order of H, and this can force the order of H to be a little bit larger. Right? The order of H must be divisible by 4 and by 3, so the order of H must be divisible by 12. In fact, the order of H has to divide the order of S4. So we're using LaGrange's theorem in reverse here. We said the order of H has to be divisible by 4 and divisible by 3, since the order of an element divides the order of the group. So that forces the order of H to be at least 12, to be divisible by 12. But in fact, the order of H itself is a subgroup of S4, and so the order of H has to divide the order of S4, which is 24. So the order of H is a multiple of 12, and it divides 24. We conclude that the order of H is either 12 or 24. And if we want to conclude that H is all of S4, we just have to argue the order of H cannot be 12. So that's the last thing we have to do here. And this is where we have to get a bit resourceful. So what we need to recall, and this is actually, if you don't recall this is a cute application of this formula for the order of the group is equal to the number of cosets of a subgroup times the order of that subgroup. But if you don't recall, you can use that cute little argument to figure out that a group of permutations is either all of its elements are even, all the permutations are even, or exactly half of the permutations are even permutations. So this is the fact that we're going to use. And so we're going to take a look at the group H, which is a group of permutations, and we're going to note that H contains the permutation 1, 2 by our hypothesis, and 1, 2 is an odd permutation. So because our subgroup in question contains an odd permutation, it must be the case that we're in this latter situation, and exactly half of the members of H are even permutations. Now, if we're assuming that the order of H is 12, then when we take a look at the subgroup of even permutations of H, we get a subgroup. It has order half of the order of H, which is 6. And so here we are, we're sitting inside of H, and the collection of even permutations inside of H is a group of order 6, just of even permutations. So that is, it would be a subgroup of A4, which is the set of all even permutations inside of S4. And so what we would have in this case is that this subgroup of even permutations inside of H is actually a subgroup of A4 that has order 6. And luckily for us, we just proved on the last page, the last slide, that no such subgroup exists. And so it cannot be the case that the order of H is equal to 12. Now, I normally have a set of summary slides in our slideshows, but here we were just really working some extra examples to hopefully help you feel more comfortable with Lagrange's theorem. So I hope that after working these examples, you feel ready to work some problems on your own.